Hello everybody. Today I will present you how to make a tree and use a BFS and a DFS algorithm in JavaScript. So before starting, I will just show you what tree structure is. So basically, it's a way of presenting data. You have a root, and the root can have children, and each children may or may not have other children, and so on and so forth. And each node can have that data inside. It can store data. So let's start coding. Let's make tree.js and tree.html. So first start coding the HTML code. Yes. Tree.js, and we will add the JavaScript code here. Okay. That's it for the HTML code. We can close it. Let's create a class for nodes. Each part of the tree is a node. This is a node, this is a node, and a node is basically just data and a link to other nodes, the children's. So how do we present this? We just have to create a constructor and a value. It will be called each time we create a new node, and this will basically have just the data and a list of children list, and that's it. We just need to add the function that will add children inside the list. Children, and the children will be basically another node. This that children list that push, and we push the children inside the list. And basically that's it. We have the node structure that which help us make a tree. So now we will make the tree. So now let's make, thanks to this class, let's make the tree. So let's create a variable named A, and it's a new node, and the value can be anything. Var B, new node. Let's make this. We will try to reproduce this picture. So A, B, C, D, E, F, G, H. C, D, E, F, G, and H. And put here whatever value I want. It's not important. Then we can let it like that. So now we have the node, but they are not linked. They're just node parts. And Now we will create a link. So a that add children. We will the a node here have 3 children, B, C, and D. So we add B and we add C and we add B. Wait a second. Now B have also children. Children, it's I think E and F. C don't have children, and I think it's D. We have G and H. So D that add children, and we can add the F, the G and H. So basically we have the tree. We have created a tree, which is in fact just node with link to each other. This is, we can say this is just that. When we say tree structure, it's just node which contain a value and a link to the other nodes. And it's we have roots and we have childrens. That's the way a tree is made. So now we need a way to check the value of the tree. How we can do this? So essentially there is two main algorithms to search a tree: the breadth first search and the depth first search. The breadth first search will check line by line, and starting from the roots, it will check the first children, then the second, then the third. Then when he finishes to check this line, it will go to the second line. You will go here, 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 and here. So it will search closest nodes first, then the nodes that are at a longer distance at a second time. But on the contrary, the BFS, the DFS algorithm will go at a dip, then come back here, go here, then go back here, 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 here. It will go at a dip at first, then it will backtrack. With this algorithm, it will search the distance node first before searching this one, maybe. So it's a different approach. Let's code this. First, let's make the BFS algorithm. So we have the tree, which in fact is the root of the tree. So we will send this inside the function, and it will be able to display everything inside it thanks to the link. So it will use the queue data structure, okay, and we push the tree inside it. And will this queue is not empty, so the length is bigger than 0. It will do the algorithm. I wrote the algorithm and I explain later. So it will display the value of q is q dot shift. So it will display the value of q. So thanks to that, we can now know what is inside the different nodes, and then it will add for e equals 0 e to q that children list that length. So for each children of q, we will add them q dot push to the list. Q dot children list dot e. So now let's test this out. Okay, let's open this. Okay, now we can see that it displays every single node. To know which one are which one, we will do maybe like this. This will be much clearer. And we should have them in order: A, B, C, D, E, F, G, H. So let me explain to you how this works. A queue structure, it's something that is like this, like a waiting line. You have this woman, which is the first in, and she will be the first to get out of this waiting line, and this guy he's the last one to enter in the waiting line, and he will be the last to get out of the line. So the first which enter to the line will be the first to get out of the line. So it's a data structure. So it's something like let's say we have an array, something like that, and if we add let's say 2, it will become this, but the first which will get out, if we add another data like, I don't know, 9, it will become 9. But if we take out data, the first to get out will not be 9 or 2, it will be 5. So we take this and it will become this, and this one. The array will become this, and we can do this in JavaScript thanks to the shift function. Shift function will take out the first the first in the array, the first element in the array, and it will give to us. So basically it's this line of code. So here we add A to the queue, to this list, and we make a list, in fact, and so we have A, and then here we take out the A and we put A inside the queue value. And I just made a small mistake, but it's not important in JavaScript. So we display its value, and then every children of A will push them in the queue. So it's A, then it's A is taken out, so we add B, C, and D. This is the children of A. Then the second round, we put we shift B because it's Q. It was the first to enter, so it's the first to get out, and it's inside Q. And we do the for loop. It have two children, so the new at the end we have C, D, and E, and F, because B is out, and now C is at first position, D is at second, and we added the children of B, which is E and F. So this is a new structure, the new array, and then it's we take out C because it's shifted, and C don't have children, so it didn't add anything to the queue. So now it's in turn to D. Sorry. We take out D, and D have two children, which is B and H. So we add it to the list thanks to this, to the push, and now we take out E. Thanks to this line, and it's taken out, but it didn't have children, so we don't add anything. And at every line, at every loop, sorry, it will check if the queue is empty or not. It's not empty, not empty, not empty. So it's continue, and then here it's check for F, but F don't have any children, so it is shifted, but it didn't add anything. And here the same for G and for H. Oh, sorry. So we have H, and H don't have any children. It didn't add anything to the list, so we can say that it stopped from looping, and the BFS function is finished. So we have displayed everything inside this, and let's have finished looping. Basically, it started here. It's add every children, this one, this one, this one, and to the queue, and his children was the first to the queue, so this one, and he didn't have children, and this one have two children, and this was added later and later, and that's why we displayed in this order. So that was basically it for BFS algorithm. So now let's make the BFS algorithm. BFS, and we also add the root or the tree, whatever. But now we will use a stack like structure instead of a queue. I will code and I will explain it later. Okay. Current node tree stack. Oh, that's not what I want. Stack that push current node, and will the stack is not empty, superior to bigger than 0. We get equal to take that pop area it's for loop equal to 0 to as that children list document stack that push is that children list, and basically we will push from the end of the list first. It's not big difference, it's just change the order of the things, but it's not it didn't change the algorithm much. Yes, and to start from the end, we need to get the length of the current node. Console let's look as that value, and I think it should be it. DFS, and I think this we should get the algorithm A, B, E, F. Okay, I will just show you this tree and this one. Oh fuck. Okay, this here. So basically we start with the A, then we go to B, then E, then F, then C, then D, then G, then H, and that's what it does. It go to the depth first, and then it go to the one near. Depth first search. That's why it's named like that. So we use a stack. I will explain what stack is. It's also a data structure like queue, but it's not working the same way. It's working like a stack of dinner plates. We have plates like this. We can add in the plate. You can add plates, but if you want to take plate, you can't take this one. You have to take the one on the top of the stack. So it's first in but last out. In with this one it was first in, first out. But if this was a stack, it will be something like this. This one is here, it will go first. Then this woman would be the last to get out. She will need to all these people to have all these people out to get out of this stack. So basically it's like this. And in JavaScript we use pop to make this happen. So let's take this example and okay, you have 5, 4, 7, 8, you add 2, okay, same. Adding to the list, to the stack is the same as adding in the queue, but the difference is when we take out. If we take out, this will not become like this. It will be, we will take out the 9 first because it was the last answer. And if we continue, you can guess it, it will be 2 to get out. So it's work differently. And so on until we come to 5. So okay. So what happened? We add A to the current node and we add it to the stack. We have this A on the stack, and the stack is not empty. We take A from the stack, it will become this at this point. It is stored in the node is stored in the S variable, and we check every children of the S node, which is A for instance for this moment. So and we add them to the stack. So the stack become and we start from the end, and so it's become, let's have this, it's become D, C and B. So D, C and B, and we print out the value. We could also print out this value at this moment, it didn't change anything, like we have done here. So it's basically the same. So at this moment, S is equal to B, and we take out this B because it's the last to enter, and so it's the first to get out. And so it's stored in S, and we add the children of B to the stack, which are E and F. C, E, and F. And D, now we add, we take out if F don't have children, E don't have children, C don't have children, but D have children. So it's become D have 2 children, which are G and H. So we make this H don't have children, so we can take it out without adding anything to the stack. And here also we can take out the G, and D we can take out because no, sorry, it was taken out at this moment. Sorry. After C was taken out, D was also taken out. But we just after this, it was stored in the S, and it was this children was added to the stack. So the algorithm stopped here at this moment because there is nothing inside, and it's displayed the tree, and it's displayed the tree at like this with depth for search. Okay, and you can change this to make it like this. It will work the same, but on the other direction. Instead of doing this, it will do this. So let's watch it. Okay, A, G, H, G, C, B, F, and E. It's start from the right side. That's the reason why I started from the end. If I take this out and this out, I will just show you something. And if we take this out and we put this here, just to check it still works. So it works the same. As you can see, this both algorithm is the same. There's only one port which is changing, and it is this port. This is the pop and this is the shift. That's the only thing that is changing, and that makes all the difference. There's another way to make this algorithm. The DFS algorithm is to make it recursively, and you will see it's much faster to do it this way. Just take a few lines of code, read its value, and for each children, for y equal to 0, tree that's length. For which children you just call the function itself. It's a few lines of code, and if we try this, we should get the same result. Oh no, I forgot something. I forgot this, I think. Oh no, I forgot. I don't forget this. I think the return is not mandatory, but it's not a tree length, it's tree.children list length. Oh, I forgot to make the tree equal to tree children. What? I forgot something. Oh yes, we need to send the children. I do. My bad. This is we send the children, not the tree itself. to the algorithm recursively, and now it should work. Okay, too much recursion. Oh, what the fuck? E. I think I didn't save. My computer will burn in this infinite recursion. Okay, I might need to reopen this tab. Okay, give me that. Infinite loop. This was this. And we got stuck inside an infinite loop. And now, as you can see, we have the right way, the right display. It's working fine. So I will just briefly explain how does it work. Maybe I should use the debugger. So start running. So it stopped here, the debugger, and let's go next step. So the value of create was A. Oh, I should add it here. Can I add? Okay. Okay, now nice. We have the tree, and for each children of a tree of a node, it will call this one, and so it will do the same, and until we found out a tree or a node which don't have children, it will come here, and the function will, the DFS recursive function will stop and will go to its parent, and so the parent will continue the for loop. It will go to the next children until every children don't have children, and they will come back to their parents. So basically it's like we have a return here, but it's not mandatory. The DFS function come here, it starts for the children, and for in the children it go inside the other children, and when the children have finished, have returned, it come back here, and when the for loop is finished, it return, so it return to the parents. That's basically how it works. Okay, and that's like it. It's a stake, but here the stake is not explicit. It's implicit. It's the system that makes it. So that's what it, guys. I explained to you how to make a node and how to make a tree in JavaScript. It's pretty easy, nothing very hard. And I explained you how to make the BFS and the DFS algorithm, and also the DFS algorithm recursively. So thanks for watching. Have a nice day.